Good morning. Our team number is 9003H. I'm Galileo, she's Chung. We are from Poland called Centenary Leung Memorial College. The title of our project is called The Expressibility of Cosines as Sum of Bases. Why do we come up with such a problem? This is because of a problem of a mathematical Olympic that is CHAMO. Prove that. There's the thought exists PQR being rational number such that cosine 2 pi over 7 equals to P plus square root of Q plus cube root of R. The official solution to this problem use the Gauss rational theorem and some basic theory of polynomials were inspired by this problem. Therefore, we want to generalize this as followed. That is, for which opine P cosine 2 pi over P equals to A0 plus A1 up to AN, where AI equals to DI to the 1 over PI. DI are rational number. PI is the ith pi, and PCO equals to 1. We want to solve this problem by a similar method as that of the original problem. However, we failed. Therefore, it's a must to seek alternative or even advanced rate. We are inspired by our advisor that cosine 2 pi over P actually equals to theta P plus theta P inverse over 2, where theta P equals to the primitive P of duality, that is e to the 2 pi I over P. Therefore, we associate this problem with the cyclotomic field, that is Q adjoint theta P, which contains Q adjoint theta P plus theta P inverse, which contains rational number. And we know that the degree here is P minus 1. The degree here is 2. So, by Taylor property, we know that the degree here is P minus 1 over 2. Now, we can translate our problem algebraically as follows. That is, for which prime opprime P, we let a field K that is Q adjoint all the AI, where AI is not a rational number. That means that DI is not a perfect P power. For which prime K would contain this field. And we notice that the degree here is N, which is product of distinct pi number. So, N is square free. And the degree here, we have just shown that the degree here is P minus 1 over 2. There are two key steps to achieve our theorem. The first one is to notice that Q adjoint theta B over Q is a cyclic extension. So all its sub-extensions are cyclic as well. Therefore, there is a property of cyclic extension. That is, if Q divides P over 1 of P minus 1 over 2, that is Q adjoint theta P plus theta P inverse over the degree of here. Then there exists a field such that F is contained in Q adjoint theta P plus theta P inverse, and the degree here is Q. The second key step is to prove that this field F actually equals to Q adjoint AI, where PI equals to Q, that prime number. Yeah. How do we achieve this? We prove two things. The first one, we prove that the norm of AI belongs to the Q adjoint AI. Second, AI belongs to Q adjoint the norm of AI. Proof for one. Since norm of DI, DI is the rational number, therefore it's from the ground field. So we take the norm, that means that we take the power of the degree here. On the other hand, we know that DI actually equals to AI to the power of Q. That is, using the multiplicative property of norm, we have that equals to norm of AI to the power of Q. So we refer back to the field diagram here. Sorry, I didn't draw it actually. But anyway, the degree here actually equals to N over Q. That is by the Taylor property. So we have norm AI equals to DI to 1 over Q to the N over Q. And DI to 1 over Q is AI. And N over Q is an integer. So we are done for the first part. And the second part is easier. That's because we notice that N is square V, so Q and N over Q are coprime. Therefore, there exists integer xy such that AI to the 1 equals to AI to the Qx plus N over Qy. That is AI to the Qx times AI N over Qy. AI to the Q is DI, which is a rational number. And AI N over Q, we have just shown that this is the norm of AI. So we know that AI actually equals to a rational number times the norm to our integral power. So we are done for the second part. So by 1 and 2, we can conclude that Q adjoint AI equals to Q adjoint the norm. And we use the fact that norm belongs to the ground field. So Q adjoint AI equals to Q adjoint the norm would be contained in that field. Oh, sorry. Moreover, we know that F over Q, the degree here is a prime number, Q. Therefore, in order to have a sub-extension here, it would be either equal to F or Q. So if it's not Q, then it must be F. So we are done for the lemma. So what remains is to notice that. So what we have so far is that Q adjoint theta P contains Q adjoint theta P plus theta P inverse, contain F equal to Q adjoint AI, contains the rational number. We know that Q adjoint theta P over Q is a Galois extension and is abelian. So all its sub-extension is also Galois. So including the is Galois. So we know that F actually equal to DI to the 1 over Q. So in order to make it Galois, Q has to be 2. And we have just mentioned that N is square V, so P minus 1 over 2, which divides N, is also square V. And Q divides P minus 1 over 2 is the only divisor of P minus 1 over 2. So D actually equals to P minus 1 over 2. That implies P equals to 5. Moreover, when Q adjoint AI equal to Q, then that implies Q actually equal 1. So P equals to 3. So what we have shown is that in order to achieve our initial problem, P, the prime number, has to be either 3 or 5. So that is what we have done for our project. Thank you very much.